Okay, so next we're going to look at section. Let me copy the diagram so you know what we're trying to do over here with the diagram. So we have found the forces on AB and FG, right? So we know that this is our F1, and over here we say F1 is equal to F4. So now we are trying to find what is our F2, and F2 is also equal to F3. Okay, so from here we want to determine F2, okay, in section BD. Okay, section BD. So we want to find QBD, right? So let me draw the region of interest first, okay? So this is our AB, right? And then this will be our BD, right? So this is our point A, point B, and point D. And over here, I'm going to draw our centroid. So this is our centroid. And then we also know that this is our distance 2A. Is it 2A? No, this is A. And the distance from here to here is also A. Right. So now is this section that we're going to find. Okay. Sorry, I do apologize. I should have done this. Okay. So now we are going to go to X Z, because our transformation. Okay, sorry. This is our Y, and then this is our Z. Okay. So now our Z is moving that way, right? So now we want to find the first moment of area, QBD. To find QBD, you have to include QAB plus by QBD, right? And a QBD is going to be a function of Z. Well, this over here is a constant, because our variable Z is not acting on AB, right? It's a constant already, okay? So AB, QAB, right? So we want to find what is QAB now, right? So the width is equal to A. Sorry, the width, what am I told? The width is equal to T. The depth is A. And the Y bar is 3A over 2, right? That is for section AB. For section BD, the width now is Z. The depth is T. And the Y bar is equal to A. Okay. So this will be equal to 3 TA squared divided by 2 plus by TAZ. Okay, plus by TAZ. So I can factor out, I'm going to take out my TA. This will leave me with 3A over 2 plus by Z. Okay. Then everything is the same. That is our QBD. Then we substitute about the shear in section BD as a function of Z. So now the limits changes, right? Why? Because this is 0, and the distance from here to here, this distance, it is 2a. Okay, so if you look at the diagram, okay, so this is 2a. Okay, so now this will be 0 to 2a, right? So we have no, I'm finding the shear force first. Sorry, the shear stress. So V over I, right? And the thickness is T, right? Q will be equal to TA. I'll put in a big square bracket. TA 3A over 2 plus by Z. Okay, and I can get rid of the T, so you have B over I, right? And then A 3A over 2 plus by Z. Okay, and then so now once we get this, we can find our F2, which is equal to our F3. So the limit is 0 to 2a, right, as I explained earlier. So 0 to 2a, and then shear in section BD as a function of Z. And then this has to be area because we are using shear stress, so T dz. Okay, so now again it's just really simple integration. So this will be equal to V over I. I'm going to take out V over I. I'm going to bring A out also and the T out. Right, then we integrate 0 to 2a. Then we have 3a over 2 plus by Z, and then dz. Okay, right. So integrating, hold on, let me write this better. It looks like a mess at my end. Right, so 0 to a, so is equal to 3a over 2 plus by Z, okay, dz. So this is equal to V TA over I, right? So will be equal to 3az over 2 plus by 3az z squared over 2. Okay, limits covered is 0 to 2a. Okay, so this will be equal to V TA over I. So this will be equal to 2 times 3. So it's divided. So this is 3a squared, okay, plus by 4 divided by 2a squared. Okay. So this will be equal to 5 TA cube, 5 BTA cube over I, right? 5. Yep. So I, okay, so I, we did find I before. So 5V TA cube over I, so it's 28 over 3 TA cube. So this will become 15 over 28, right? V, because this and this cancel. Okay, so this is equal to your F1 is equal to F2 is equal to F3. And then finally, we're going to take moment. Okay, so we're going to take moment now. Okay, so let me So we're going to take the moment at point C. Let me copy the diagram first. All right. So this is our point C, right? And then these are our F1, F4. This is our F2, F3. Why the direction is that way? Because it's controlled by B. Right, so this is our V through point C. Right, so the V through point C, you don't need to find ED, is because it's exactly going through the center of point C. That's where we're going to take our moment. So there's no perpendicular distance. Okay, so what we know is F1 is equal to F4. So this is equal to 5V over 56. And then we have F2 is equal to F3. And this is equal to 15V over 28. Right. So we are doing the final stage. Okay, so find the shear center. Okay, so far we want to find the position of the shear center. Right, such that the structure will deform without twisting, right, under unsymmetrical loading. So we are going to take, so if we draw our transformation y, z, okay, and this is our rotation in a x, right? So we will take moment, summation of moment in the x direction at point C is equal to 0. Okay, so we're going to take the moment at point C, where I'm circled in red now. Okay, so we will have F1, right? So F1, if you look at how the arrow is moving, it is moving in a clockwise direction. Yes, Lord, right? It's relative to point C, right? Relative to point C, right? F1 is going to generate a clockwise rotation. F2 will also generate a what? Clockwise rotation. So you know that F1 is equal to F4. So this is minus 2, right? And then the perpendicular distance is 2A. Oops. And the force of F1 and F4. So this is F1 and F4 is 5V over 56. Okay, that's 5V over 56. And then F2 and F3 are doing, so F2 or F3 are doing a counterclockwise rotation. So it's plus, right? So this is plus 2, because there's F1 and F2 and F3, sorry. The perpendicular distance is A, and this is equal to 15V over 28. And then the final one, okay, so we are going to have a load V coming down here where the shear center is, right? So that V over there is equal to V times E, and is going to generate an anti-clockwise direction. So plus by VE, the whole thing will be equal to 0. Okay. So VE is equal to, so 2 times 2, 4.